Hello and welcome to another video on kinematics. Imagine you're in your car, you're driving down the road, and you're passing through town, you have to keep it slow. Slow, easy, 30 miles per hour. And then leave town and you go to an open country road, and suddenly it leaves that 30 miles per hour, and you see the sign that says you can do 55. What do? You step on the gas, you give an extra energy, little oomph to your car, and you start speeding up. You have a positive change in your speed, positive change in your velocity. They're increasing. What do we call that? What do we call that change in velocity or change in speed? Well, in both cases, we refer to it as acceleration. One, the change in speed, is just a number. It's how much is it changing by, how fast is it changing by. On the other hand, we have acceleration, the vector, which is the change in velocity. It tells you what direction you're speeding up or slowing down in and is measured and given a direction. The difference between the two is confusing on many levels because it's the same term both ways. But ultimately, whenever you hear the term acceleration, you should be thinking about something slowing down or speeding up. Let's take a look at how this looks visually. Now, in the Pivot Interactive, we watched this puck go, and as it went and moved, we could actually, starting from the beginning, watch it speed up as it went on. Notice how it's slow and getting faster as it goes down the ramp. Let's watch that again. Standing still, and then it speeds up as it goes down the ramp. What this is it's changing its speed, it's changing its velocity, it's undergoing what we call acceleration. The direction of the acceleration in this case is down the ramp. It is going along the ramp, pushing it down. Now, in this particular case, we say it's without friction, without any other things causing acceleration, which is a complication we'll have to deal with down the road, but for right now, it's the only thing we need to worry about. So the acceleration here is constant. Because the acceleration is only caused by one thing, in this case, gravity, what causes all things to fall, it's constant. Without that friction, the acceleration due to gravity is constant. Now, whenever we have acceleration, always, we're going to have something causing that acceleration. We're going to have some outside influence causing that acceleration. Something pushing, something pulling. This can be a direct contact, like your foot pushing along a box, or the engine which is connected to your car providing acceleration. Or it could be indirect, acting at a distance via a field such as gravity, electric field, or the such. We'll deal more with those later, but understand that whenever there is an acceleration, something has to be causing it. Acceleration doesn't come out of nowhere. If I drop this remote, it's going to fall because of gravity, not because that's its natural tendency. So, acceleration is this change in velocity, change in speed. How do we measure it? Well, it's a little difficult to do directly. If we're looking at the positions, we can't get at the acceleration, not easily, unless we cheat. Now, we'll talk about how exactly we cheat using a graph like this in the next video. But to start, we're going to look at a data table and how we can figure out the acceleration from that. You might remember this graph from our homework where we did a straight line through it, found a trend line, and got an approximation. Now that we've talked about linearization, though, we can see that there's a curve on it. If I put the trend line on this graph for a second, I can see the curve fairly clearly. These are all bottled on one end. These on the outside are curved to the outside. So I know that there is some change in the velocity, some acceleration. So let's go ahead and take a look at this and find the acceleration. The easiest way to do this is to find our velocities first, or in this case, since we're talking distance, our speeds. Speed is measured in meters per second. And while we can't get the exact speed at any given point, what we can do is we can go, okay, well, if we just look at these 2 points, just these two, I can find the slope between these 2 points, and that'll be the speed. It won't be a perfect fit, but it'll be a good enough fit for me to get some numbers. So in this case, what I do is I subtract my distance traveled and divide by my time. With a computer, I can set this up to be automatic. I won't be able to get a first data point for this section here because I don't have anything to compare it to, but everything else from then on I can. So I'm just going to set up a formula really quick, like so, and it'll do all the work for me. Now you'll notice that I could divide by the difference in my time between these two sets. And if I just copy that down, I have my speed, or my average speed over that section. Now, once you have your speed, you can go a step further. The change in your speed, the rate your speed is changing at, is your acceleration. We measure that in meters per second, or meters per second squared. And again, I can do the exact same kind of thing with the difference between my cells, divide by my change in time. Now this is an approximation. It's not going to be flawless. It's not going to be unstoppable. But it will get us the job done. And if I carry it through, what I'll find is that my acceleration is roughly constant. In some cases, it's a little bigger. In some cases, a little smaller. But it's almost always right around 9.8. So the rate that my speed is changing is my acceleration. Now, if I were to do the same thing, but instead of having a distance, having a displacement, having a speed, I have velocity, I still get acceleration, but I have a direction with it. In some cases, this could be up, down, left, right, or whatever. But regardless of how you get there, the rate at which it's changing tells us information. Let's talk about how we could get this information graphically. I can also get the same data by graphing it, looking at the speed versus time, or if I had velocity versus time of an object, which will give me the acceleration. If I'm looking at speed, it'll just give me a number, but if I'm looking at the velocity, it would give me the vector value. Now, acceleration can be positive or negative. Something could be speeding up or slowing down. We use the term acceleration through these interchangeably. It's just a positive or negative, an increasing or decreasing acceleration. You'll occasionally hear the term deceleration, which for slowing down, which, while appropriate, is often seen as superfluous. I will largely use the term acceleration for any change in speed or velocity, but if I happen to use deceleration, it's because I'm specifically referring to something slowing down, which tells you something about the problem or what we're looking at. With that said, let's summarize everything we've learned to date. When we're talking about motion and how things are moving, we care about 4 things. How far does it move? How fast is it moving? And how is that how fast changing? And time. Time isn't on here because it's just t. It's t. Doesn't particularly matter. There's no special term for time. We have scalars, which are just numbers, and we have vectors, which are numbers or magnitude or values with a direction. We have our distance, which is how far in scalar terms. Just count all the legs or the such as you go. Or you can talk about displacement, which is always going to be your change in position, your delta x. Final minus initial. You might see this written as xf minus xi, or x minus x naught. X naught being your initial or starting, x being wherever you are at the moment you're solving for. Your speed is how fast you're going in scalar terms. It's what you see when you look at your car. It's your speedometer. Whereas your velocity is how fast in your direction. Typically, you'll see this measured in meters per second for this class. You might see miles per hour, but really any distance per any amount of time. If you wanted to get really technical, you could do light years per minute. You can go as small as picometers per year. These are all scales. It's always a distance over time, whatever that unit might be. The last we have acceleration is how is that changing? You talk about rate over time here for that, but a common way you'll actually hear this, someone talk about the acceleration, is 0 to 60 in 3.3 seconds. That is how fast it can get to 60 miles per hour. That is a acceleration, even if it isn't reported as such. That in this particular class, you'll often see meters per second or meters per second squared. That is that. There's also the vector value, but the vector will have a direction. Positive, negative, left, right, up, down, towards the center, something. Some other notes. Distances, meters, or typically meters or miles. Speeds, meters per second, miles per hour. Acceleration, meters per second squared, is the most common. There are other examples that we will talk about briefly. Vectors, you will often see them notated with this arrow on top. If I write arrows, that's just me indicating it's a vector to myself. Don't worry about it too much. It is fairly common to leave it off and just say V or A or delta X. But do know that in strict proper parlance, you need to have that arrow. If this chart helps you understand things, copy it down, please. I'll put up the units and then leave a final frame of it.